Okay. All right. So I hope you guys can see the slide that I'm sharing. So for our today's topic, we will see how the reaction involving electrophilic aromatic substitution. Um, Basically, this is, I think last semester, what you have learned is electrophilic addition reaction and also nucleophilic substitution reaction. But with regards to aromatic compound, it doesn't undergoes addition reaction. Instead, it only undergoes substitution reaction. And the uh, species that involved is an electrophile. Okay, since the aromatic compound, later we'll see how what is the determination of an aromatic compound. So aromatic compound is basically electron rich. So when it wants to react, it prefers to react with an electrophile. So at the end of this, somebody is joining. Okay, so at the end of this lesson, students should be able to give an introduction to aromatic compounds. So you will learn how to determine whether a compound is aromatic, non-aromatic, or anti-aromatic. Okay, uh, and also the concept of aromaticity using benzene as example. So benzene is one of the most simplest example of aromatic compound, and it is widely used in a lot of our daily compound. Okay, it doesn't matter if it's in pharmaceutical or even in other material like plastics or anything. So then after that, we're gonna go into the reactions. Okay, the mechanism. What is the mechanism? First, we're gonna see what is the mechanism. Actually, the mechanism is quite simple. It use the same general mechanism for all of the reaction involved, like halogenation, nitration, sulfonation, and so on. Okay, and we will also see the various effect. This one we will continue next week. Okay, the various effect of substituents on the orientation and reactivity. That means if the benzene ring already has a substituents or substituents um, on the structure, it will somehow affect the reactions that happen. Okay, the electrophilic aromatic substitution reaction that happens. Then we will see the relationship between aromatic structure and their reactivity, whether the substituents will make the structure more reactive or less reactive. And last is the relationship critical to understanding of how biological molecules or pharmaceutical products, agents are synthesized using the very reactions that you will learn. Okay, for introduction, first you need to know what is an aromatic compound. Then, how are you going to differentiate whether a compound is aromatic or not? The opposite of aromatic is aliphatic. Okay, I think this one you have learned last semester in your nomenclature topic, I think in chapter 2. Okay, so one of the properties of aromatic is it contains very strong odor, aromatic odor. Okay, as some of the I think you managed to do the what you call experiment of unknown organic compound. One of the tests is to check the odor of the compound, okay, the smell, but it may not be that accurate, okay, but then again, it is one of the key or the first things that you can check for a chemical compound, okay. Then it must be, the structure must be fully conjugated cyclic. How does it mean by conjugated? Conjugated meanings it contains this double bond and single bond, then double bond again, okay. And it also must be in cyclic. Cyclic is like this, in one cycle. It is not in open chain. Or even it can be polycyclic. Poly meaning more than one cyclic structure. Okay, it can have 2 benzene ring attached or 3 benzene ring attached, which will be learned in another topic. Okay, and the structure is planar. Planar meaning it is in 2D, 2 dimension. The all of the carbon and hydrogen are in 2 dimension. Later, if we have time, I'll try to show you using an software to 3D to see the 3D structure of uh, what you call that, benzene. And it must obey Huckel rule, which we'll see later. What is Huckel rule? Okay, this is very important. It must obey Huckel rule. And the simplest example of an aromatic system is benzene, which what we will be used throughout the whole unit. Okay, benzene will be used as an example. So the structure is of benzene. It contains 6 carbon, 1, 2, 3, 4, 5, 6. Okay, with 6 hydrogen as well, 1 hydrogen at each carbon. Okay, it may look similar to a cyclohexane. Okay, but cyclohexane, each of the carbon contain 2 hydrogen, and the structure, as I think you have, you managed to try to do it in the lab using the 3D model. Okay, the structure of cyclohexane, it is not in planar, it's not in 2D. Okay, it can have the chair conformation or the boot conformation, in which all of the carbon and hydrogen are not in one plane. Okay, you have the axial position for the hydrogen or the equatorial. So aromatic, why does the name aromatic? Okay, why was it named aromatic? Because previously in the old days, the smell is used as one of the characteristic to classify this organic compound. So aromatic was used to describe some fragrant compounds in the early 19th century, but which is now we know that it's not accurate or correct. So later they are grouped by chemical behavior. So unsaturated compounds that undergo substitution rather than addition. Okay, unlike alkene or alkyne, which can undergo addition reaction in unit 6, electrophilic addition reaction. Okay, what you have learned in your second semester. So nowadays, it is distinguished from aliphatic compounds by electronic configuration. Electronic meaning it involves electron. Okay, one. Okay. Then we have over here example of we have benzene, and also we have uh, benzene with substituents. Okay, the first one here we have uh, carbonyl group C double bond OH. Okay, so it makes this benzene into an aldehyde, and the name has become benzaldehyde. And here it has one methyl group attached to the benzene structures. Okay, the name it is known as toluene, or it can also be known as methylbenzene. Okay, its sources and names of the aromatic hydrocarbon. So normally they are obtained from high temperature distillation of coal tar, or what we call as thermal cracking. Okay, they are just separated using heat. Okay, in temperature distillation, that means you will heat this whole very thick black sort of semi-solid, okay, in which that at different boiling point, each of the components will start to boil, so they are collected that way. Okay, so here you have benzene with boiling point of lower than water, which is about 80 degrees Celsius. Okay, slightly higher than ethanol. Ethanol is normally around 73 degrees Celsius. Then once you add a methyl group, okay, a methyl group, it become a toluene. So the boiling point increase to 111 degrees Celsius. Then we have these structures, okay, in which you have two CH3 group, but one of the CH3, what do you call that? This methyl group is sticking out from the middle. So why does this structure sticking out from the middle? While all the while we know that it must be bonded to a carbon, but now it is drawn sticking out from the middle. Find out about this. So this will be your first tutorial question. When you have two CH3 group, it is known as xylene. Okay, then this is known as fuse ring. When you have two different ring attached together, this is indene, and we have naphthalene over here, in which two of the what you call benzene ring are attached together, fused together. But when they are not fused together, they are known as biphenyl. Bi is two, and you have the benzene ring. Okay, when it becomes a substituent, it is known as phenyl. Later we'll see the nomenclature. This is when you have three benzene ring attached together. Okay, we have anthracene and also phenanthrene. This 1, 2, and 3 will be in a different unit, okay, which is known as polynuclear aromatic compound. Then this is some of the compound that are available in our body, probably that contain the benzene ring. Okay, first we have this adrenaline and also ephedrine. So it is a hormone released by the body to respond to stress. So adrenaline, it makes you slightly agitated. Okay, you suddenly become energetic or something like that. Okay, or epinephrine. So this is the structures, and we also have this chloramphenicol, which is an antibiotic used to treat typhoid fever. So it contains this benzene ring here, making the whole structure and aromatic. Then we have this mescaline, an active ingredient which can be obtained from peyote cactus, okay, from a tree basically. So a natural product, okay, which is an aromatic compound. So you see the structures contain 4 substituents. Okay, you have ether group 1, 2, 3, and then an amino group over here. Okay, this mescaline also has these psychoactive properties. Okay, probably to treat you call that something about brain diseases, something like that. Then we have this fenfluramine and also phentermine, which is a psychostimulant drug used to suppress appetite. So basically this is your pil ubat kurus. Okay, so once you eat this, then you won't feel hungry. So if you won't feel hungry, you will not eat. So it is very effective, okay, to treat obesity or something like that. But then again, it has side effect to your heart, okay, to our heart, in terms of fibrosis, and also it will lead to heart attack and your and untimely death lah. So you manage to reduce your weight, but at the end of the day, you're gonna get a heart disease. Okay, normally it's very famous in the US back in the 80s and also early 90s, but nowadays they are already banned. Okay, these two combination. Normally they are eat together. Then we have this antioxidant used in food, BHA and also BH3, okay, to make your food last longer. Okay, so that so this is also can be classified as a preservative, okay, to make our food last longer. Then an artificial sweetener, saccharin, okay, to those person that is diabetic, so they cannot consume normal sugar that contain glucose, fructose, and so on. So they can use this artificial sweetener like saccharin, or sometimes now we also have this what you call as stevia. And somebody is joining. And we have this P, or also known as para. Later we'll see what is P. Dichlorobenzene in mothball and air freshness. Okay, ubat gegat. Okay, this is another form of it. And we also have this amphetamine, also another type of appetite suppressant. Then we have methamphetamine, speed, which is sometimes also used as recreational drug. Okay, methamphetamine, amphetamine. This also sometimes used as recreational drug. Okay, the only difference is you see the number of, the here you have another CH3 at the end. Okay, here you have NH2, and over you have NHCH3. One metal group is being replaced here. Hence the name stands for methyl. And then we have aspirin. Okay, this one you have synthesized in the lab last time. Okay, used as in same to treat like fever or headache, something like that. And disinfectant, hexachlorophene. Then we will go to see the Huckel rule. So this is very important. So please pay attention. So what is Huckel rule? So Huckel rule is one of the besides all the properties that we learned in the first slide. So these are one of the most important thing you have to check for a compound if it is to be an aromatic. So in Huckel rule said that a planar cyclic, okay, planar in one plane like benzene, cyclic conjugated pi system will be aromatic. Okay, will be aromatic when it has 4n plus 2 pi electrons. If it does not fulfill this 4n plus 2 electron, even though it is planar, cyclic, and conjugated, it won't be aromatic. So what is this 4n plus 2 pi electron? That means the pi electrons that is available in the whole structure equal to 4n plus 2. This is just simple arithmetic or algebra. So n must be a whole number. Okay, whole number meaning nombor bulat. 1, 2, 3, 4, 5, 6, and so on. You cannot have 1.1 or 1.5 or 2.5. No, it must be a whole number. So sp2 hybridized carbon will has a pi electron. So in benzene, there are 6 carbon which is sp2 hybridized. So in total, it has 6 pi electrons. So how are you going to confirm whether this benzene ring is aromatic or not? Is by using this 4n plus 2. So 4n plus 2 equal to 6. So 4n plus 2 equal to 6. Then you try to get the number of this n. If n is equal to either 1, 2, 3, 4, 5, and 6, so on, then the structures is said to be aromatic. So for example, we have 4n plus 2 equal to 6. So you bring these two to the other side. Okay, then it will be, wait, I'll try to use a pen. So 4n plus 2. Sorry, yeah, I'm using equal to 6. So when you bring 2 to this side, then it will become minus 6 minus, sorry, 2. Then 4n will become or will equal to 4. You have 4n here. So n will be 4 minus 4. So if you bring 4 to this side, then it will be divide. So 4 divided by 4 equal to 1. So n equal to 1. So when n equal to 1, 2, 3, and so on, that means it fulfills Huckel rule. So benzene is having 6 pi electrons. So benzene is aromatic compound. Later there are some other example I will show. Okay, so aromaticity, the relation of aromaticity and the Huckel 4n plus 2 rule. So this benzene ring is unusually stable. It is very stable. Hence, it does not react to addition reaction. Instead, it just want to substitute one of the hydrogen with another electrophile. Okay, if it's not stable, then this double bond can be easily broken. Okay, in fact, in alkene, double bond is actually not that strong. So, but why does in benzene the structures is very stable? So, heat of dehydrogenation is 150 kilojoule per mole, less than negative than a cyclic triene. Okay, planar hexagon, all of the bond angles over here, this is the bond angle, is 120 degrees. And the carbon-carbon bond length, this length, okay, all of the length between each carbon is 139 picometer. The size, the lengths are all the same. And it undergoes substitution reaction rather than electrophilic addition. One of the reasons is due to the resonance structures. Okay, resonance hybrid with structures between two line bond structures, which you have learned previously. So this provide extra stability to the whole structure. Okay, compounds with 4n pi electrons are not aromatic. In fact, it can be anti-aromatic. What does it mean? You can also have other compounds that is planar, cyclic, and also conjugated like this. You have double bond, single bond, double bond. But then again, it does not fulfill Huckel rule of 4n plus 2. Okay. This, for example, here you have 4n pi electron. The number of pi electron is 4. Okay, how do I know? Here you have 4 carbon, 1, 2, 3, 4, and all of these carbon are sp2 hybridized. So in a way, if you see a double bond in a compound, that means these two carbon over here will contain 2 pi electron. Okay, 2 pi electron. So that means one double bond will be equal to 2 pi electron. So this whole structures over here of cyclobutadiene, it contain 4 pi electrons. So if you put into the equation of 4n plus 2 equal to 4, then that n is not a whole number. Instead, it fulfills this formula of 4n. Okay, 4n equal to number of pi electrons. So they are less stable. Okay, less stable. They will distort out of plane and behave like ordinary alkenes. So it behaves like ordinary alkenes. So it can have the addition reactions. So 4 and 8 electron compounds are not delocalized. Okay, not delocalized. So cyclobutadiene is so unstable that it dimerized by a self-Diels-Alder reaction. So the dimerize, it means self-addition. When you see the word dimerize, it means self-addition, that it undergoes addition reaction with the same structures. Okay. Then you also have this cyclooctatetraene has 4 double bond, the one below over here. Okay. Change to laser. Okay, this one, 4 double bond, it can react with Br2, potassium permanganate, and also HCl as if it were 4 alkene. So this whole thing, even though it is planar, it contains 4 conjugated and it's cyclic. It does not fulfill the Huckel rule of 4n plus 2. So these are known as anti-aromatic. When it fulfills the 4n equal to the number of pi electron, then it is anti-aromatic. Okay, a non-aromatic, if you have non-aromatic, it does not fulfill 4n plus 2 or even 4n. Okay, if you get the n different, then it cannot be used in 4n or 4n plus 2, then it is non-aromatic. Okay, aromatic does not only must be a neutral compound. It can be an aromatic ion as well. Okay, so the 4n plus 2 applies to ions as well as neutral species. For example, here you have anion and also cation. So both are aromatic. So how? So both of the cyclopentadiene anion and the cycloheptatriene cation are aromatic. So how to make sure whether it is aromatic or not? First, you have to check the Huckel rule, 4n plus 2. So here you can see there are 2 double bonds. As I said earlier, 1 double bond equal to 2 pi electron. So here you have already 4. But at this C carbon, this C, you have these 2 extra electrons over here, which are on the p orbitals. Okay, or which are in p orbitals, and these are also counted as pi electrons. Okay, since it is not being used or shared with any other substituents or even hydrogen. Okay, so these two are counted as pi electron. So in total you have 2, 4, 6. So 6 can be used in this 4n plus 2 rule, in which when you do the calculation, you're going to get n equal to 1. Okay, if n equal to 1, the number of pi electron is 6. If n equal to 2, number is 4. Number is 10, number of pi electron. So it will increase by 4. Okay, 6, 10, 14, 18, 22. Okay, you just plus 4 because the n here is times by 4. Okay, and then for cation, you have 2, 4, 6. Okay, here this carbon lacks electron, so it does not contain any extra electron in the p orbital. Okay, hence there are only 6 pi electron, and it is in cyclic, planar, and conjugated. So it fulfills the aromatic or aromaticity properties. So here you have aromatic compound 1, 2, 3, and the one below is not aromatic. So the first structure is benzene, of course. It contains 2, 4, 6 pi electron. So 2, 4, 6, n equal to 1. Then for the second structures, you have 2, 4, 6, 8, 10. So if you put this into the 4n plus 2 equation, you will get n equal to 2. So that means it fulfills Huckel rule. And this one, this is naphthalene. This is anthracene. Sorry, phenanthrene. We have 2, 4, 6, 8, 10, 12, 14. Okay. So it is in the increment of 4, 6, 10, 14. So this one also, if you put into the formula of 4n plus 2, you're going to get n equal to 3. So these three are aromatic. But the one below here is cyclobutadiene. The number of pi electrons is only 4. So it cannot be used in the 4n plus 2, but it fulfills 4n equation, same as this one. Okay, you have 6 pi electron, 10, and also 14. Here you have 4 pi electrons, and also 8 pi electrons for this one, which is not aromatic. Okay, question. This will be your tutorial. Okay, I'm gonna show you one example that contain a heteroatom. Okay, what is heteroatom? Heteroatom is atom other than carbon and hydrogen. For example, you have oxygen, nitrogen, sulfur, and it must be included in the ring. So that is considered heteroatom. If this oxygen is a substituent, then it is not an heteroatom. Okay, there will be a what you call a specific unit or topic for heterocyclic compound. Okay, example. I'll give one example. This one. So for these structures, as you can see, there are already two what you call double bond. So each of the double bond contain 2 pi electrons, correct? So here you have 2, then you have 4. But don't forget to check each of these heteroatoms because it may contain lone pair. For example, oxygen will have 2 lone pairs. What is lone pairs? If you forget, try to look back. What is lone pairs? Lone pairs meaning it contain electron 1, 2, 1, 2. So it has these 2 lone pairs available on this oxygen. Okay, how I know there is 2 lone pairs? Go back to your Lewis structures. How to draw your Lewis structures? This is just based on valence electron because oxygen, the valence electron is 8. Once it is in a bond, it must has 8 electron, the octet rule. Okay, so 2 over here, 2 over here with this carbon. So there are 4 more. Okay, and since this is neutral, it is considered to be neutral. So I know there are 2 lone pairs over here. So one of these lone pair electron are in the p orbital. Okay, how do I know? Same answer, Lewis structures. Okay, if you draw the electron, it will be in the p orbital. So this lone pair that is in the p orbital will be counted as pi electron. Okay, this one no. Only these two electrons that are in the p orbital will be counted as pi electron. Hence, the number of pi electron is over here you have 2 and then another 2, 4. So this is another 2, 6. So now you check with the 4n plus 2 rule. 4n plus 2. Whether it fulfills this equation or not. Okay, 6. If you put over here, then you're going to get n equal to 1. So this structure over here is actually an aromatic compound. Okay, so take note of this nitrogen, sulfur, oxygen, and this nitrogen as well, whether they contain any lone pairs or not. Okay, so this will be your tutorial as well. So then we're gonna go into the nomenclature or naming. So most of the benzene that contain a substituents will have common names, and these common names are acceptable to IUPAC. Okay, for example, you have methyl benzene, which is known as toluene. Methyl benzene, if you have one methyl group CH3 attached to the benzene ring, so it is known as toluene. Then you have aminobenzene. Aminobenzene, amino NH2 attached to the benzene ring, so it has another common name which is known as aniline. Okay. Then you have these monosubstituted benzene systematic names as hydrocarbon with benzene at the end. Okay, for example, if you have bromine attached or chlorine or iodine, then it will be known as bromobenzene or chlorobenzene or iodo or fluorobenzene. So the name benzene will remain at the end. And if you have nitro group, then it will be known as nitrobenzene. And this one, if you have another aliphatic chain attached to the benzene, then it will be known as propylbenzene. Okay, this one, 1, 2, 3, propane. Since it is a substituent, then it will be known as propylbenzene. Okay. If this chain is longer than benzene, that means more than 6. Okay, here you have 6, 1, 2, 3, 4, 5, 6. If this chain is more than 6, then the benzene ring will be the substituents. Okay, so common names of some of these aromatic compounds. So when you have CH3, it's known as toluene. If you have hydroxy group, it will be known as phenol. Okay, so this is an alcohol, so it will be known as phenol. This one is aniline. And this is if it become an ester, so acetophenone. A ketone. Sorry, this is a ketone. Acetophenone. C double bond O over here, and then you have R, C double bond O R. So this is acetophenone. And aldehyde, okay, C double bond OH. And if it become a carboxylic acid, C double bond O OH. And this one, if it contains two alkyl group or methyl group, if you have one methyl, the name is toluene. Two methyl over here, it is known as xylene. And the last one is styrene. So this is the starting material for the polymer known as polystyrene. Okay, the name is polystyrene. Normally you just say polystyrene, polystyrene. But the pronunciation, if you know that it is known as polystyrene. Okay, this is the starting material in which the polymerization will happen between this C double bond C. Okay, and then you have another structure over here that will continue. So it become polystyrene. The phenyl group or phenyl group. So this happens when your benzene ring is a substituent. So a benzene ring, when it becomes a substituent, it is not known as benzyl. Yeah? Take note, the term is phenyl. Okay, when you have C6H5 dash. Okay, benzyl refers to C6H5CH2. So this is benzyl, but this is phenyl. Okay, don't get confused over here. So this is phenyl, this is benzyl. So you use phenyl when the chain is longer than 6. For example, here you have 7. 1, 2, 3, 4, 5, 6, 7. So it will be known as phenylheptane. 2 phenylheptane because the benzene ring is attached at the second carbon. So now we will see what does it mean by this. Earlier you have seen these letters in front, O, M, and P. So it stands for ortho, meta, and para. And it is only used when you have di-substituted benzenes. Okay. So the first one, which is ortho, it only can be used if you have substituents on adjacent carbon, which is carbon number 1 and carbon number 2. Example, here you have chlorine on adjacent carbon, side by side. Okay, doesn't matter the position, it can be between this one and this carbon, or this and this. As long as it is side by side, then you can use the prefix ortho, dichlorobenzene, so that it is known that the position of benzene is at carbon number 1 and carbon number 2. Okay, then you have this meta. Meta, that means the carbon is at position 1 and 3. 1 and 3. It is separated by 1 carbon. So meta dimethylbenzene or metaxylene because it contains 2 CH3. Then we have P, stands for para. Para is separated by 2 carbons if the position is at carbon number 1 and carbon number 4. Carbon number 1, carbon number 4. Okay, carbon number 1 and carbon number 4. So example, instead of writing 4-bromotoluene, so you can just put P-bromotoluene. So when you see here P, we know that it is a para. So the position is 1 and 4. And all of these, O, M, and P, if you use, it must be written in italic, okay? Slightly slanted. So this is italic. Para, meta, ortho must be written in italic. And remember, this can only be used if you have di-substituted. If there's only one, you cannot use. If it's more than 2, for example 3, 4, also you cannot use. Okay, can only be used when you have 2 substitution. If there is more than 2 substituents, so you have to use the same rule like other nomenclature as well. Choose numbers to get lowest possible values. That means numbers in the ring so that the numbers will be lowest possible value. For example, like the first one, the name given here is 4-bromo-1,2-dimethylbenzene. So that means the numbering starts from this CH3. So 1, 2, 3, 4. Okay, so it cannot be 1, 2, 3, 4, 5, 6. So this will be number 6. So you cannot do that. So try to give the lowest possible number. Or in fact, you try to use this as number 1. 1, 2, 3, 4, 5, 6 also cannot. Or 1, 2, 3, 4, 5. So this one also cannot. Okay. Even if you want to start with bromine also, 1, 2, 3, 4. So this one will be number 3, number 4. So also not advisable. So this is the best way. So list the substituents alphabetically with hyphenated numbers. So even though this CH3 is positioned at number 1, okay, number 2, but when you write, you arrange it alphabetically. So bromine goes first since it is B. Okay. Then you have here dimethylphenol. So common names such as toluene can also be used as a root name, as in TNT, this one. Okay, you have 4 substituents, 3 nitro group, and also 1 methyl. So the toluene can be used as root name instead of you writing 2,4,6 trinitromethylbenzene. Okay, so this is TNT. You know what is TNT used for? This is explosive material. So structures and the stability of benzene based on the molecular orbital theory. So here you have, it is stated, benzene will react very slowly with bromine to give bromobenzene, where Br, this Br will replace one of the hydrogen over here. This is substitution rather than the rapid addition reaction common to compounds with C-double-bond-C, which is alkene. Okay, so it does not undergo electrophilic addition reaction, but it undergoes substitution. This suggests that in benzene, there is a higher barrier. Okay, we still remember about activation, energy, and all that. So this is sort of like a barrier for benzene to obtain this addition product. Okay, if you see over here, this product is not formed. It does not form. Instead, you're going to get this, whereby all of the double bonds retain. So how to prove that inside benzene it contains this extra stability? So this is based on experimentation, okay, through heats of hydrogenation. So this is used as indicators of stability. If you look at the energy level graph over here, here you have hexane, cyclohexene, and then 1,3-cyclohexadiene, and you have benzene. So let's take a look of normal cyclohexane. The energy level is very low. When it is at a very low energy level, that means the structure is very stable. Okay, hence this is all sigma bond, so it must be very stable. Then you have cyclohexene. So addition of H2 to C-double-bond-C will give off 118 kilojoule per mole of energy. So this negative means it is an exothermic reaction. So it releases 118 kilojoule of energy. If this one, cyclohexadiene, 2 double bond, so theoretically it will release 118 times 2, you're going to get 236 kilojoule per mole. But experimentally, the data obtained is 230. So still acceptable, just a difference of 6 kilojoule per mole of energy. By right, if you have 3 C double bond C, you should get about 356 kilojoule per mole of energy being released. Okay, but the actual result that is obtained is the heat of hydrogenation release is only 206 kilojoule per mole. Okay, there is a difference by 150. In fact, it is lower than the one with 2 double bond. Okay, so therefore it has about 150 kilojoule more stability than an isolated set of 3 double bond. So this is the results of uh, structures of benzene itself. Okay, here you have all of these contain resonance. Okay, one double bond, two double bond. Anything that contain double bond, triple bond may form resonance form. But in benzene, it has this extra stability with regards to the resonance structures. Okay, how? So all of its CC bonds are of the same length. Okay, one of the reason is all of the carbon-carbon bonds are of the same length, 139 picometer. Then all of the electron density are the same in all of the carbon. So here is a representation using a software, a chemical software, okay, in which we can predict the electron density or the electron cloud in a compound. So the one in red, meaning that the electron is where it is mostly situated. Okay, blue, less electron. So that means over here, the electrons are located in the middle, here in the middle. Hence, back in your school days, benzene is drawn this way, used to use a circle. But now in your undergraduate, this one is not acceptable anymore. You must draw it this way using all of double bonds. Okay, so this circle is trying to indicate that the electrons inside the benzene ring is always moving. Okay, it is located in the middle. Then the structure is planar. Okay, unlike these two, this is not planar. Okay, structure is planar and all of the CC bond angle is 120 degrees. Okay, and each of the carbon is sp2 hybridized and has a p orbital perpendicular to the plane. Okay, if you see it like this, then the p orbital is sticking out, okay, from the screen since it is perpendicular. This is explained using MO, okay, molecular orbital. So here you have 6 carbon. Okay, one carbon will contribute 1 p electrons in the p orbital. We have 1, 2, 3, 4, 5, 6, and all of that electrons are bonded. So they are in bonding area. So we have 2, 2, and 2. Okay, so none in non-bonding and also none in anti-bonding. And the orbitals with the same energy are degenerate. So this one, okay, they are all having the same energy level. Okay, so that is all on the sort of like introduction of aromaticity and also the what you call the structures of benzene. Okay, this part on the reaction, I'm just going to go a little bit here, okay, in which that the substitution reaction of benzene and its derivative. Derivative, that means if it's contain any other substituents, okay. So these are the reactions that you have to know, except phenol, since phenol will have a whole topic for itself, okay. There are halogenation, nitration, sulfonation, Friedel-Crafts acylation, and also Friedel-Crafts alkylation that you have to know. So in total, there are 5 reactions: 1, 2, 3, 4, and 5. But all of these 5 reactions will have the same mechanism. I mean, like the general mechanism is the same. So you have to, if you know the concept of the general mechanism, then you should be able to know the mechanism for each of these reaction. Just for this week, I'm just go into the bromination first. Okay. electrophilic aromatic bromination or halogenation. Okay, this example is using Br. Okay, so benzene pi electron will participate in the reaction as a Lewis base. Okay, in reaction with Lewis acid. Lewis acid is the electrophile itself. So the product will form by a loss of proton. So as you can see here, okay, this step, okay, this step is only for bromination. Okay, this is what you call the step before the actual mechanism happen. So starting from here, okay, from here, the mechanism is the same for, this is considered to be step 1. Yeah, step 1. Okay, the only difference for all of the 5 what you call reaction is this one, because this is how the electrophiles are being prepared, or sort of, I would say, like this is the preparation step in which electrophiles to obtain the electrophiles. Okay, so the first step, you have benzene. The benzene will go and attack an electrophile. So in this case, if you look here, you want it to react with bromine. Okay, Br2. Br2 is not, how to say, polarized, because Br minus, Br minus, it will break into 2 Br minus, Br minus. So electrophile is not electron rich. So how does this bromine can be turned into a slightly positive bromine? So one way to do it is by the help of a catalyst, iron bromide. So the function of this iron bromide is to turn this bromine into this intermediate. Okay, this intermediate. This intermediate will contain this bromine that will act as an electrophile. See, you have Br plus, and also this whole thing minus, FeBr4. So once you have this, then only your benzene can have the reaction. Okay, if you put Br2 without the addition of iron bromide, the reaction may proceed, but at a very, very slow pace. Okay, in fact, it may not happen altogether. So with the help of this catalyst, so it helps to prepare the bromine into this intermediate. So once it has this bromine is form this complex with iron bromide, then only the electron-rich benzene can react. So the first step is the electron from one of the double bond will be given to this bromine. So this bromine will be bonded to this hydrogen. So this one will be removed altogether. Okay, so it will form this intermediate cation. So all of these are known as arenium ion, okay, or also known as delocalized cyclohexadienyl cation. So why cation? Because you have a positive ion over here, and it forms resonance structures, okay, in a way that the electrons move around, okay, the ring. So it forms these three what you call intermediate, okay, or resonance structures. So this is step 1. Then the second step, this is your second step. So the second step is earlier you have this Br plus and FeBr4. So the FeBr4, which is the anion, okay, this part, okay, this whole thing is the anion. will come in and take the hydrogen away. So it will take the hydrogen. So the electron from this carbon hydrogen will be shared back into the ring. Okay, it will be shared between this carbon. So this carbon, instead of now it is lacking one electron. Once it receives electrons from this carbon hydrogen bond, it will form back the double bond. Okay, and you have this HBr as byproduct, and this is your catalyst. Remember, catalyst does not change form. Okay, this can be used again for another reaction. Okay, the cationic addition intermediate transfer a proton to FeBr4 minus. Okay, this restores aromaticity in contrast with addition alkane. So if you look at this energy level diagram, you have this addition and substitution reaction. So this is the okay. If you want to obtain the addition product, as you can see, the energy level diagram, the one in pink color, okay, is at a very high level compared to a substitution product. In fact, the substitution product has lower energy level than the starting material of benzene. So these substitution reaction are very much preferred compared to the addition reaction. Okay, so this is for bromination. If you want the reaction to proceed with other halogen, for example, chlorine and iodine, okay, fluorine is not doable in a lab because the reaction is too reactive. Okay, chlorine and iodine can produce aromatic substitution reaction with addition of other reagents to promote the reaction. Okay, for chlorination, what you need to add is iron chloride. Okay, for bromination, you have to add iron bromide, FeBr3. But for chlorination, you have to add iron chloride, FeCl3. The function of this iron chloride is the same. It just want to polarize this chlorine, Cl2, okay, into Cl plus and Cl minus. Okay, once it has that polarized chlorine, then only benzene can attack to become electrophile. So iodine, if you want to have iodine as the halogen, so it must be oxidized to form a more powerful I species, I plus. So iodine normally form iodide, I minus, but now you want to make it into an I plus to lose another electron. So you must use copper chloride, CuCl2, okay, to turn this iodine into a I plus. Okay, once you have this I plus, this is considered to be electrophile. Remember, electrophile, it can be neutral species and also all positive species, okay, cation. So the same step will be used. All right. So for the slide, I'm going to stop here first for this week. Okay. Let me